So, but then slowly increasing, so few thousands, okay, 2,000, 3,000 totally overall, of course. For this big country, it's not a big number, but we don't know whether it will be in this level or it will be increased.
Yes. And it's also is unclear whether in Germany all people are really registered, or I think it's a hidden number, a large hidden number.
Yeah, that's true.
But we have not many restrictions anymore.
Yeah, here also, but travel seems to be somewhat risky. Okay. Yeah. I have not yet started traveling much, only yeah, locally. But, yeah, younger people are all traveling.
Okay. Yeah, it's really risky. That's right.
Yeah.
Especially in the plains, and so one does not know. And it's have a lot of circulation of all this air, and so
yes,
the airport. And I think the same in the trains.
Yeah, sure.
And what is the weather now? It's already warm. And
it's quite warm. Yeah. So it's,
let's wait a few minutes.
yeah.
People are coming now. Yeah, Sujit wrote you that he cannot participate today.
Hello.
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 Hi.
Nice to see you.
Nice to see you.
Should we start or should we wait a minute? What do you
I think we can start. So it's exactly the time.
It's exactly the time. Okay. Okay, then let me start today. I'm the chairman. Professor Tsuchit cannot participate due to very serious family reasons. And I'm very happy to start our seminar today. You know, we have this special seminar series, which is rather successful, I would say. We went over several areas already. And today we have a very important speaker, but let me give a few general remarks at the beginning. Please turn off your microphones and please use this question and answer box to ask questions or to announce that you have a question. Then after the talk, we will call you and you can ask your questions and personally, or I can read, whatever it's better for you. So I think you all know our today's speaker, Professor Lakshmanan. He is, of course, has a special positions, awards, and so he is Professor of Eminence and National Science Chair at the Bharatidhasan University near Trichy. And he has really made a lot of fundamental contributions in nonlinear dynamics, in conservative systems and dissipative systems. But what I think is really his most pioneering role, he started and initiated nonlinear dynamics very early in India, in this place, Trichy. And he has built up a school in his place, of course, with a lot of scholars distributed now along India, but also worldwide. But he also initiated at several other places in India very successful studies in nonlinear dynamics, and of course also initiated a lot of international collaborations. Many people visited this very nice city. I visited also several times. I can recommend you to go there. And he also started schools on nonlinear dynamics in India, which is also very successful series now. Also we are really very happy to have him. And of course, he is very active. And today he will give some of his recent results on integrability and chaos in simple and complex nonlinear systems. Professor Lakshmanan, please, you have the floor.
Okay. Thank you very much, Professor Jürgen Kurz, for your very kind introduction. And so it's a great pleasure to give a lecture in this very interesting seminar series. And I have such a long collaboration with Jürgen. It's really a pleasure that he spoke such kind words about our center, about our city, and so on. Now let me go to share my slides. Yeah, let me start sharing. I will share my screen. Yeah. And are you able to see my PPT, Ankit?
Yes, Professor.
Yeah, I will go to full view. Yeah. Yeah, let me start my seminar. Integrability and chaos in simple and complex nonlinear systems. Collective dynamical states. So there has been a very large number of past and present students collaborating, postdoctoral fellows and colleagues, including my mentor and my supervisor, PhD supervisor, Professor P.M. Mathews. There are a large number of students and postdoctoral fellows and colleagues. So since the list is large, I'm not presenting individual names. But overall, what I want to discuss this evening is to bring out the nature of, provide a broad overview of the nature of collective dynamical states in integrable and non-integrable, and particularly chaotic nonlinear systems and networks. I hope to introduce different kinds of notions, including solitons of different forms, rogue waves, bullets, vortices, and then bifurcations and chaos, desynchronization, synchronization, different types of chimeras, and so on, with specific examples. Basically, in my lecture, I will divide it into three parts. The first one, I will discuss about integrable systems and the notion of solitons in 1+1 dimensions, nonlinear dispersive type. Then I will also consider the non-integrable versions in 2- and 3-dimensional, 3-space dimensional systems, introduce the notion of optical bullets, vortices, and so on, and what their interaction behavior and when they can exist, and briefly I will point out. Then in the second part, I will move on to simple nonlinear dissipative systems, their bifurcations and chaos, particularly some of the dissipative, nonlinear dissipative systems we have introduced in the literature. And then we consider networks of these dissipative systems and consider various collective dynamical states, including various kinds of synchronization, chimeras, and other collective dynamical states. So this is the broad overview of what I am going to present today. I don't need to introduce to this audience that the evolution of dynamical systems are in general represented by nonlinear differential equations of different types, ordinary, partial difference, integral differential, delay, and so on and so forth. And the underlying equations of motion are broadly divided into integrable dynamical systems and the non-integrable dynamical systems, integrable dynamical systems with sufficient number of integrals of motion commuting, Poisson bracket sense, commuting integrals of motion, and non-integrable dynamical systems which do not possess sufficient number of such integrals. And then a very important class, namely chaotic dynamical systems. So they are all of interest in our study, starting from simple to complex systems, including networks. So here I will consider some of the natural integrable dynamical systems to start with and generalize them to exhibit bifurcations and chaos and complexity with the introduction of additional forces. So let me start now with the class of nonlinear integrable dynamical systems, namely nonlinear dispersive systems of certain types, leading to the notion of solitons and integrable nonlinear partial differential equations or ordinary differential equations, the so-called soliton equations and their initial value problem, Cauchy initial value problem. So I'm sure all of you are familiar with many of these nonlinear evolution equations, nonlinear dispersive wave equations, starting from the famous Korteweg-de equation, the third order nonlinear partial differential equations for the amplitude u of xt. X and t are the independent variables, u is the dependent variable. So here in this notation, suffix means partial differentiation with respect to that particular variable. So du by dt plus 6u du by dx plus d cube u by dx cube equal to 0, the Korteweg-de equation. And as all of us know, that it emerges as the limiting form of the equation of motion describing the unharmonic lattice, namely the Fermi-Pasta-Ulam lattice. And then one knows what is the consequence of this Quatermain-Debris equation. Then similarly, you have many other equations, the modified Quatermain-Debris equation, the Sine-Gordon equation, nonlinear Schrodinger equation for the complex valued function Q. So IQT plus QXX plus or minus 2 mod Q square Q equal to 0. For example, for describing the electromagnetic wave propagation, intense electromagnetic wave propagation in optical fibers, in optical medium, nonlinear optical medium, or the ferromagnetic lattice, the dynamics of ferromagnetic lattice, the classical Heisenberg spin system for a spin vector S of xt, unit spin vector with 3 components. So you have ds by dt equal to s vector product d square s by dx square. Again, it's a limiting form of the discrete Heisenberg spin chain. But you can also have discrete integrable nonlinear dynamical systems like Toda lattice equations or Ishimori spin equation and so on and so forth. So nearest neighbor, exponential interaction, or many component, 2-component wave propagation optical systems, the so-called Manakov equations for 2 modes, Q1 and Q2, 2 complex modes, and so on. So there are various generalizations in different directions, and even in higher spatial dimensions, and so on. But all these systems have several common property. They are solvable. Their Cauchy initial value problem is solvable by identifying 2 linear differential operators, namely the so-called lax operators, and then carrying out the so-called inverse scattering analysis. You find the general solution can be expressed in terms of n solitons. And there you can have breathers, lumps, rogue waves, and so on and so forth. So all these dynamical systems are completely integrable, infinite dimensional in general, or large number of dynamical variables. So you have infinite number of integrals of motion, lax pair, soliton solutions, various integration techniques, etc. Constitute, underlie these various nonlinear dispersive systems. And you also observe that these equations are integrable only when the dispersion, so you have the dispersion for equation in the Quatermain-Debris equation, for example, you have the dispersion term d cube u by dx cube. And this has to be balanced appropriately by nonlinearity. So balancing between the dispersion and nonlinearity in a specific way leads to all these integrability properties, this very nice collective dynamical states like solitons, breathers, and so on. If you change the nonlinearity to u cube, for example, you do not have these kind of properties. You require very specific structure, either ux or u square ux with appropriate coefficients, etc. Similarly, for the nonlinear Schrodinger equation, you have the dispersion term QXX, and this has to be compensated by this kind of nonlinearity, mod Q square Q. And then only you can have this kind of integrability properties. And what is the underlying structure? So let us consider the case of nonlinear Schrodinger equation, IQT plus QXX plus 2 mod Q square Q equal to 0. Where Q is complex valued, consider its initial value problem. You can write down 2 lax pairs, 2 by 2 lax pairs, and then you can carry out the inverse scattering analysis. I will not be able to go into the details. But for appropriate initial conditions, you can have, for example, the simplest solution, the one bright soliton. Because you have this plus sign, you have the bright soliton in the sense you have asymptotically, you have the solution vanishing sufficiently fast, but in a narrow region, in a localized region, you have non-zero intensity, a non-zero amplitude. So you have one bright soliton. If you have a negative sign here, the nonlinearity in front of nonlinearity, you may have dark soliton. That is, in the constant background, you have dip in the intensity of the light. So intense electromagnetic wave propagating in a Kerr medium, cubic Kerr medium, leads to this nonlinear Schrodinger equations, and this T and X stand for the normalized propagation distance and time, retarded time, and so on. But you can get the one bright soliton solution in this exponential form, ratio of exponential forms, which you can write in terms of hyperbolic secant H function. So Q of xt, the complex valued function, can be written as K1R, the amplitude, and a modulation term, and secant H K1R, x minus 2 K1IT. So the dynamics of the solution can be represented in terms of the wave variable eta 1, which contains K1x plus IK1 square T, where K1 is the wave number, complex wave number, the real and imaginary part. And the amplitude is the real part, and the velocity corresponds to the imaginary part. And when you plot mod Q square, instead of Q, you plot mod Q square, the intensity, you find the localized structure. You start anywhere at T minus infinity to go to T plus infinity. You see a localized pulse propagating without change of form or diminution of speed. And that is a solitary wave. And it turns out to be a soliton because you can get even more general solution, namely the two bright soliton solution, which you can again obtain by appropriate methods. For example, simple analytic methods, so-called Hirata's bilinearization. There exist many other methods, Darboux transformation, etc. Or you can carry out the inverse scattering transform analysis. By any of these methods, you can get two bright soliton, for example, in this form. It's slightly complicated in terms of two wave variables, eta 1 and eta 2, and with propagation constants K1 and K2. With appropriate constants occurring, lots of constants, let's not bother about it. But when you plot this function, mod Q square, you find asymptotically for large negative T, you have two localized pulses as the initial condition, and they start propagating, and as time progresses, they make a head-on collision. After a collision, they come out without change of form or diminution of speed. Both the solitary waves, they retain their structure, except for a phase shift, finite phase shift. So it's just like a billiard ball collision. And so solitary waves now become solitons. You can generalize this to 3 soliton, n soliton, and for general arbitrary initial condition, you can solve the Cauchy initial value problem as n solitons in the background of dispersive waves, linearized dispersive waves, which in any case, as time progresses, they disperse and die down. So asymptotically, the general solution corresponds to these n solitons. You can consider even more general equation, namely coupled nonlinear Schrodinger equations. Two modes, Q1 and Q2, they are coupled by, you have the nonlinearity mod Q1 square, self-phase modulation, and cross-phase modulation, corresponding to intense electromagnetic pulse propagation of birefringent fiber or two-mode optical fiber wave propagation. Again, this equation one can show admits is a completely integrable Hamiltonian system. It possesses a Lax pair, 3x3 Lax pair, 3x3 matrix Lax pair, n bright soliton solution, infinite number of conserved quantities and integrals of motion and conservation laws, and so on. Let us consider the bright soliton for this two-component case, the single bright soliton in the two components Qj, j equal to 1, 2. You find, again, you can express just like in the case of nonlinear Schrodinger equation, you can express in terms of these exponentials, which you can rewrite in terms of, again, secant H function. Except there is a difference now. You have an additional constant appearing, the unit polarization vector, A1 hat, A2 hat, and this A1 hat is expressed in terms of two complex valued functions, alpha 1, 1, alpha 1, 2. So that you have this A1 and A2 corresponding A2, and these two variables constitute a unit polarization vector. the presence of this unit polarization vector, in addition to the amplitude which occurred in the case of one component nonlinear Schrodinger equation. Well, it's very interesting possibility. So, for example, you can have in the two modes, again, localized structure, secant H square form for the intensity Q1 square and Q2 square. But when you allow these two solitary waves in the two modes, Q1 and Q2, to collide, again, as in the case of one-dimensional case, they undergo head-on collision. But after collision, you find, because of the presence of this unit polarization vector in this particular form, A1 in this particular form, you find there could be intensity redistribution among the solitons in the two modes. So, for example, the soliton S1 in the first mode can gain energy, while the second mode can lose energy, and the opposite can happen in the second mode for the soliton 1 and soliton 2. But the total intensity in each of the solitons is considered when you consider the total intensity in the first mode and the second mode for the soliton 1, similarly for the soliton 2. And this collision, the change in the amplitude occurs in a particular, satisfying a particular law, linear fractional transformation, which means it forms a group. So for every action, there is an equal and opposite, there is an inverse action possible, which leads to construction of, fascinating such shape-changing collision or intensity redistribution collision can occur in two-component, multi-component nonlinear Schrodinger equation, which allows the possibility of constructing optical logic gates. As I said, this collision follows a linear fractional transformation law. So when this intensity redistribution occurs, and these solitons, resultant solitons can again go and interact with a third soliton. So in which case, the original state can come back. So you can construct optical logic gates. And as a consequence, optical computing becomes feasible through this light-light collision. So this has been experimentally verified, this energy exchange collision, intensity redistribution collisions. And we have generalized this to an n-component case, and the logic gates, etc., have been constructed. It is at this stage, we also realized very recently that you have two components in this particular form. But if you consider the linearized version, you have Q1, IQ1T, Q1XX, Q2T, Q2XX. So this allows the possibility, it's not only the fundamental soliton will have one wave variable, but it can also have two independent wave variables. And that led us to consider the possibility that you can have even more general solution at the fundamental level, the so-called non-degenerate soliton. So where you can have two independent wave variables, eta1 and eta2, with the corresponding wave numbers k1 and L1, which are in general different, but if they are equal, then you get back the earlier solutions, the energy exchange collision solitons I pointed out. But if they're not, you can get more general solutions in this form, exact form. But when you plot them, you can have very many interesting possibilities. You can have single hump, as I have pointed out earlier, the secant H square form, but you can have double hump in both the modes, and you can have in one mode double hump, in one mode, the other mode single hump, and you can have flat top, and very many such possibilities can exist. And then you can find that exact two soliton solutions form, and you can draw their write down their asymptotic structure, their collision properties. Very many interesting collision properties occur. It's not only in these two-component equations, but three-component, n-component equations, and many other generalizations of these integrable coupled nonlinear Schrodinger equations. In recent times, we have pointed out the existence of all these possibilities. Well, this is all good in one space, one time dimensions. But what about when you extend this analysis to two space dimensions or three space dimensions, because the real world is three-dimensional. So do these solitons exist in 2-dimension and 3-dimension and so on? But there exists analysis you can rigorously prove that this component of this class of soliton equations with Kerr nonlinearity, that means cubic nonlinearity of the form I have pointed out here, here mod q1 square q1 or q2 square mod q2 square q1, etc. They do not allow the extension in 2 dimension, 3 dimension to persist for all times and all space. So if you consider a bullet-like structure, it collapses in the case of Kerr nonlinearity. In 2 dimension, there is a critical collapse. In 3 dimension, there is a supercritical collapse, and so on. How to overcome this kind of collapse and get stable structure in higher spatial dimension? And also the point is that in higher spatial dimensions, as we have seen that collapse always occurs, are there other possibilities of generalizing this kind of optical materials, for example, in nonlinear optics? So you can consider, instead of the standard positive refractive index material, you can consider negative index materials, negative refractive index materials. And these materials are in general, they are called metamaterials. The sense they do not exist in reality, but you can design them artificially. And for example, you can consider an array of thin wires. In between, you have the so-called split ring resonators. And these can lead to negative electric permittivity and magnetic permeability. So you can design in the laboratory such negative index materials originally suggested by Penry and co-workers, and later on was realized in around 2003 by Zarov and so on. So for propagation of intense optical pulses in such negative index materials, one can deduce the dynamical equation dA by dz in this form, d square A by dt square, d square A by dx square, d square A by di square. So you have diffraction, you have dispersion, diffraction in the perpendicular direction coming in. And then you can have nonlinearity, cubic nonlinearity, and then you can also incorporate quintic nonlinearity. So all this kind of nonlinearities can be introduced explicitly in terms of this designed engineered materials. So one can have this kind of nonlinearity, and then one can try to look at the kind of structures these systems admit. So when you consider this generalized nonlinear Schrodinger equation in 3 + 1 dimension, for example, you can also consider their limiting form 2 + 1 dimension. 3 + 1 dimension, if you consider this, you can write down the corresponding Lagrangian, and then you can start with a Gaussian ansatz for corresponding to a bullet-like form, a localized structure in 3 dimensions. So you have exponential Gaussian form, exponential minus x square plus y square by 2 square plus alpha plus modulation form and an unknown initial amplitude and a chirp form. So alpha, this unknown function alpha z plays the role of chirp, and Az is the A bracket Z is the spatiotemporal radius, and phi Z is the amplitude of the beam. So you make an ansatz and you substitute into this Lagrangian and you find a reduced Lagrangian. And from this reduced Lagrangian, you write down the variational equations for these unknown functions phi, theta, and A and alpha Z. So from these dynamical equations, one can construct an appropriate potential and show that when you have purely cubic term, there will be no stable fixed point, stable equilibrium point which can occur. But when you have competing nonlinearity, that the signs of the focusing and defocusing, that is the signs of cubic and quintic terms are of opposite sign. For example, gamma 1, the cubic one is negative and quintic one is positive, then you can have possible equilibrium points. And similarly, when the cubic, the the defocusing, the cubic one is positive, that is focusing, and no, quintic one is focusing, and cubic one is defocusing form, that is the negative form, that you can have equilibrium points. So in such cases, you can deduce appropriate conditions for such equilibrium, stable equilibrium structure to exist. And then you can show by numerically analyzing this partial differential equation, you can show the existence of exact bullet-like structures. So this, I'm showing the corresponding numerical analysis, which we have carried out recent times using split-step Fourier transform analysis and 264 by 264 by 264 grid point. And if you consider an original Gaussian structure of a bullet-like form, you find when you have just cubic nonlinearity, the structure as it propagates, it breaks into, it collapses into smaller, finer structures like this. So this is a video that I point out. So you start from a localized structure, which as it propagates, it degenerates into smaller pictures. But when you have appropriate cubic nonlinearity with negative coefficient and quintic nonlinearity focusing type, positive nonlinear coefficient, then you find you start with the initial structure. As it propagates, the structure is retained. So I will point out the corresponding film. So as that the propagation distance increases, you find the structure remains for a long distance. So unchanged, the form remains unchanged. So that is the kind of structure you have. You can also ask what happens to these structures, these stable structures which exist, which can identify satisfying certain conditions which you can deduce from variational analysis. And you can ask the question, what happens when they collide? So as we have seen in the case of one space, one time dimension, solitons, localized structures collide, they come out without change of form or diminution of speed. But in higher dimension, you find they develop, they either decompose or they develop breathers or new kinds of oscillatory structures they can develop. But on the other hand, if the appropriate conditions are satisfied, when these bullets collide, they can collide. After collision, they can come out without change of form or diminution of change, without a change in the structure. So here I point out, I show you a video corresponding to collision, which satisfies the appropriate conditions on the parameters. So as they propagate, they collide. After collision, they change their shape, but if you wait for sufficient time, they get back their original shape and exactly their original shape. So except for a possible phase shift, they undergo kind of elastic collision. So even in higher dimension, for appropriate conditions, the choice of parameters of the coefficients of nonlinearity, stable bullets can exist even in 3 dimensions. But if these conditions are not met, when they collide, they will create new structures, new filaments. They degenerate into chaotic filaments. So as I have pointed out here, so which I show with this video, when appropriate conditions on the cubic and quintic nonlinearity are not satisfied, then they can undergo collision, and after collision, they can degenerate into smaller filaments, chaotic filaments. They can give rise to. So, for appropriate choice of nonlinearity parameters, the solitons, the bullet-like structures can maintain their form. You can even have stable quantum droplets, for example, in Bose-Einstein condensates, or vortex-like bullets by starting with initial wave distribution just of the Gaussian form, d power im theta for different values of m. You can try. You can again numerically integrate. So you start with a vortex or a quantum droplet of Downett form, and for suitable choice of m, the vortex index, you see that as the as time increases, they divide, they get degenerated into smaller droplets. So in general, this happens, but if appropriate conditions on the nonlinearity parameters can be satisfied, you find as this vortex starts propagating t equal to 100, t equal to 1000, t equal to 2000, they retain their form and original shape. So stable vortex-like solutions can also be, just like stable bullets, stable vortex-like solutions can also be identified. One can generalize these studies on these coupled nonlinear Schrodinger equations for actual applications in nonlinear optics, like soliton switching in PT symmetric nonlinear directional couplers, or various kinds of PT symmetric laws, introducing additional PT symmetry into this coupled nonlinear Schrodinger equations. You can also consider various the wave propagation, fiber Bragg gratings, which can lead to very interesting stable structures. So in a series of papers in recent times, we have shown the possibilities of actual applications of these kind of structures in nonlinear optics. So these are all for solitons in 1, 2, and 3 dimensions corresponding to vanishing boundary conditions. But you can also have other kinds of boundary conditions for the initial value problem, where the underlying dynamical variables go to constant values at infinity. So for example, you can have general breather solutions for the Manakov equations. So their form is complicated, but that is not important. You have both hyperbolic and trigonometric functions arising. And if you plot such structures, you find both in space and time, these are oscillating. So these are breathers. They change periodically, but then at large values of x or t, they take constant values. And a limiting form of this is this structure, rogue wave, which is a rational function in t and x. And its structure is of this form, for example, a single rogue wave. So it has a constant background, but then suddenly appears and disappears, both in space and time. So such waves, the rogue waves, can also occur in hydrodynamics, in optics, and many other situations. When you have this kind of nonlinear type Schrodinger equations, it can occur in nonlinear Schrodinger equations, coupled nonlinear Schrodinger equations, and you can have multi-rogue waves and so on. So these are all the basic collective dynamical structures that can arise in completely integrable nonlinear dynamical systems. Let me then quickly move to the other case, nonlinear dissipative systems. Again, let me consider the 5-4 equations, for example, for the Higgs boson, which is again a dispersive wave equation, phi t minus del square phi plus m square phi plus lambda phi cube equals 0. It admits wave solutions very long time back in my initial days of research. We have classified the kind of wave solutions this 5-4 equation can admit. Both plus m square phi and minus m square phi plus lambda phi cube. But these are not when you perturb. In the limiting form, for example, in this case, you can have 10H type solitary wave solutions. You can have solitary wave solution also in the limiting form of elliptic functions, but they are not stable. When two such waves, solitary waves, collide, they radiate energy and they disperse. So these kind of equations, though dispersive, do not retain their shape and form, under collision, solitary waves. Okay. And you can consider these kind of equations, and you can add additional damping and additional forcing and so on. So you can consider soliton structures. What happens to the solitons? They evolve chaotically. But you can consider simple versions of this, simplified versions of this, 0 dimension, just the time variation only. So a single oscillator. So I replace this phi by x. D square x by dt square minus omega naught square x plus the lambda x cube equal to 0. A double well potential. And you can show that it admits a dn type elliptic function solution in certain range of amplitude and cn type wave solutions, etc. You can even introduce damping minus alpha x dot. No, this is plus alpha x dot minus omega naught square x. I think this generalization of this equation, there is a wrong sign I have given. So this equation, this damped equation, for positive sign also you can integrate, and for 2 specific values only you can obtain exact solutions in terms of elliptic functions. But in general, it's not integrable. Of course, you know the most general case, the Duffing oscillator, the forced double well oscillator, external forcing F sin omega t. You know that the system exhibits interesting bifurcations, chaos structure, which is quantified in terms of the the period doubling and bifurcations and chaos. They are characterized by the Lyapunov exponent. So whenever you have periodic motion, you have negatively Lyapunov exponent, and the chaotic regime you have positively Lyapunov exponent, and so on. You can have other kinds of such oscillators, for example, the driven van der Pol oscillator, which also exhibits mode locking, quasi-periodicity, etc. Or for other parameters, even it can even exhibit chaos. And then you can have Duffing van der Pol oscillator, which exhibits quasi-periodicity, chaos, periodic windows, chaos, and periodic oscillations, and so on. So you can consider such oscillators with the addition of external forcing or damping and so on. And you can consider the coupled versions of these systems under different couplings. So what kind of dynamical structures and collective dynamical motions exist? You can have other interesting equations. The Mathews-Lakshmanan oscillator, which we have identified when I was a PhD student, without understanding that these equations are related to what is known as quadratic type Liénard equation. So you have x double dot plus lambda x dot square by 1 minus lambda x square plus omega naught square x by 1 minus lambda x square. You observe when this nonlinear parameter lambda is 0, it is just harmonic oscillator. This nonlinearity enters in a very complex way, leading to non-polynomial type evolution equations. And you can write down an associated Lagrangian as L equal to x dot square minus omega naught square x square by 1 minus lambda x square. And it's not just the standard form, it's the velocity. Similarly, you can write down the Hamiltonian, which is p square into 1 minus lambda x square plus half omega naught square x square by 1 minus lambda x square, where this canonically conjugate momentum p is not just x dot, but x dot by 1 minus lambda x square. And when lambda is positive, the motion is confined to mod x less than 1 over root lambda. So this is a velocity dependent Hamiltonian, velocity dependent potential, or in recent times this has been identified as position dependent mass. This Hamiltonian p square 1 minus lambda x square, you can write as p square by 2 into m of x, where m, the position dependent mass, is of the form 1 over 1 minus lambda x square. Such position dependent mass problem is being pursued in recent times in very many directions. And this problem itself has been generalized to 3 dimensions, n dimensions, etc. For example, Peter Higgs himself in 1978 or 79, he had generalized this to n dimension, etc. And we have generalized this in different directions. Over the past 3-4 decades, many people have generalized this in different directions. But the important fact of this equation is it's completely integrable in a very simple manner. The most general, the initial value problem can be solved for appropriate initial conditions, and you have again harmonic oscillator like solution, except that the frequency now is the amplitude dependent. characteristic feature of nonlinear equations. Okay. And the dynamics is confined. For example, lambda is positive to a region between -1 over root lambda to +1 over root lambda, or when lambda is negative, it opens up, but you can have exact solutions. Okay. To this oscillator, if we add a damping, linear damping, additional linear damping and forcing, it exhibits a very interesting bifurcation chaos structure. Period doubling, chaos, reverse period doubling, 3-period chaos, etc., etc. And this was identified by my former student Venkatesh and myself in 1997 itself, but this has been generalized in different directions even in recent times. And additionally, if you change just this sign to 1 minus to 1 plus, you have a mechanical system, a rotating particle moving on a rotating parabola. 1 plus lambda x square x double dot, and everything else is same. And this equation also exhibits very interesting bifurcation structure, symmetry breaking, period doubling, periodic windows, reverse period, chaos, etc., periodic. And in recent times, it has also been observed that in the region of crisis, it can exhibit extreme events. So, which in my department, they have identified such extreme events. We have also identified another interesting class of Liénard equations where you have only linear x dot occurs. Position dependent velocity that is occurring, x dot terms that is occurring. So otherwise it is just an unharmonic oscillator x double dot plus alpha square by 9x cube plus omega naught square x equals 0. But if you add this specific term alpha x dot, and then you find that because of this term, this is PT symmetric. Space reflection, time reversal symmetry. This PT symmetric system we have found in 2005 admits an exact integral. And as a consequence, over the years, this kind of systems we found can admit a Lagrangian description, a canonically conjugate momentum, and a Hamiltonian description. But of non-standard form. This is not kinetic energy minus potential energy, but it's more complicated form. This is also not kinetic energy plus potential energy, but some function of P into x square quadratic in the dynamical variable plus a function of P, the canonically conjugate momentum. For this particular case, it has this form. And this particular equation momentum space can be completely solved in quantum mechanics. The Schrodinger equation can be completely solved. In classical case, you can solve this equation, you can obtain general solution, but now leading to so-called isochronous oscillations. Frequency is same as that of the harmonic oscillator, but the structure shows the nonlinear behavior, very interesting behavior. To this equation, if you add a forcing and damping, it exhibits very complex motion. But if you consider more general Liénard equation with the arbitrary parameter alpha, gamma, with gamma negative, and add a forcing, it exhibits very interesting bifurcation structure, period doubling, reverse period doubling, and then a crisis, and then chaos, and quasi-periodicity, etc. Everything occurs. And here also extreme events in this region can occur. So very recently, people have identified such extreme behavior events can occur even in this simple structure, the simple dynamical equation. You have other interesting equations. Nano spin ball, spin Tark nano oscillator, a tri-layer structure of nano dimension. So current passing through such wire, ferromagnetic, non-ferromagnetic, and ferromagnetic, but all conducting. So like magnetic, cobalt, and copper structure. So in this film F1 nano film, it's magnetic, ferromagnetic. In this film F2, it's again ferromagnetic of the order. This first one is of larger size, 100 to 200 nanometer. Then this is of the order of 2 or 3 nanometers. Then as current passes, you also consider the spins, the spin degree of freedom. So they are polarized before entering, once they enter this larger ferromagnet. Then when it passes through this interspersing material, it experiences a torque. Because of the torque, the spin starts oscillating at microwave frequencies. That's what Slunsky and Berger during 1996 pointed out, the possibility of nano spin torque nanovolts, nano spin ball. And the dynamics is represented by the so-called Landau-Lifshitz-Slunsky equation. The ordinary ferromagnetic system, the continuum limit, is represented by the Landau-Lifshitz-Gilbert equation. So the Landau-Lifshitz form is ds by dt for the spin vector, the unit spin vector, the classical unit vector. S cross H effective, the nearest neighbor interactions, anisotropy, external magnetic field, everything is contained in this H effective. And then you have the damping term, the Gilbert damping term, S cross ds by dt with a corresponding damping factor. Now the Slunsky current term corresponds to S cross J, where the J is the current which can have this form S dot SP. SP is the fixed spin direction, and S dot SP leads to the spin current interaction. Now, this kind of equations one can analyze in terms of stereographic projections and so on. We have analyzed this, and when there is no magnetic field present, initial spin starts precessing very slowly, and when current alone is present, it exhibits a faster switching, and you can get exact solution. But when both are present, very beautiful bifurcation structure occurs. So period doubling bifurcation chaos for the spin variable. So here for mx, the x component of the spin variable. So you have a beautiful bifurcation structure. Now, the problem, the usage of this nanospin ball, that it can generate microwaves, but the power that is generated by a single nanospin valve is extremely low. But in order to enhance the power, you have to couple them, couple two spin valves or three spin valves, n spin valves. For example, I have coupled here two spin valves, and under appropriate conditions, it can exhibit synchronization. And you can couple 100 spin valves, for example. Very recently, we have identified that it can exhibit, initially they can exhibit desynchronized motion, but if you wait for sufficiently long time, it can exhibit completely synchronized oscillations. Because of synchronization, power can be enhanced considerably. So such coupled dynamical systems can be also considered. Finally, electronic circuits. Simple LCR circuit with external forcing. Now, to this, you add a nonlinear resistor, namely Chua's diode. Chua's diode is a three-piece linear structure. So you have the voltage H of V. So this is the dynamical equation for voltage and current. So you have C dV by dt. C is the capacitor, L is the inductance, and R is the resistor. So the current IL minus H of V because of the presence of this nonlinear resistor. And so the dynamical equation contains H of V, and H of V is not linear, but it's piecewise linear. Depending on the value of the potential, it can change its form. It's the H can have three different linear pieces. Because of this, in each of these linear regimes, it is completely integrable. But when you consider the combined form, it can exhibit all kinds of bifurcations, chaos. So this is the numerical analysis, and this is the experimental analysis, period doubling bifurcations. And this is the structure that is obtained by identifying the exact solutions in each of these pieces and then combining them at the junctions. And you get, again, exactly the same kind of structures. All kinds of bifurcations, etc. occurs. You can consider arrays of such coupled oscillators. You can consider two-dimensional arrays, and you can consider this as a kind of reaction diffusion system, and you can get all kinds of patterns And you can get spatio-temporal oscillations in these structures also. Now, in the final part, in the next, I think I will take just 10 minutes. Just I will quickly pass through what I want to say. So in the second part, I have tried to point out that there exists very many interesting integrable dynamical system of low dimension, but highly nonlinear, very surprising systems. But to these systems, if we add appropriate forcing and damping, etc., they can give rise to very complex dynamical behavior. Even now, there are lots of things to be understood, like the extreme events and so on. Now you consider a large number of such coupled systems. For example, the van der Pol oscillator, which I started in the beginning, the Duffing oscillator, the van der Pol oscillator, Duffing van der Pol oscillator. Consider a collection of such Duffing oscillators coupled in a particular way. But before that, consider a single van der Pol oscillator. Introduce multiple scales. So you have the frequency omega square minus epsilon plus epsilon omega naught square. And then you have this half bifurcation parameter. Introduce multiple time scales. And then in the leading order, you can deduce for the variation of the amplitude of oscillation in the slow scale, A of t, T1, which I call as complex, in general complex. And you can write down the corresponding value. I rewrite as Z equal to AR plus IAI. And you get the nice equation, the dot equal to A plus I omega minus mod Z square Z, where omega is the frequency. So you can consider a system of such coupled oscillators, coupled van der Pol oscillators. Then you get the coupled system of this Stewart-Landau oscillator, which was discussed in the previous lecture also. So you have a system of Stewart-Landau oscillators and coupled in particular way. For example, the global coupling in this case, okay, Zk is the mean value Zk, k running from 1 to 2n, and that is coupled to each of these oscillators. You can have other kinds of coupling. And when you introduce the Duffing part, the cubic oscillator part, then you can have here mod Zj square Zj. So higher order interactions, etc. So you have a collection of such Stewart-Landau oscillators coupled in appropriate way. You can have different kinds of couplings. You can have local coupling, you can have global coupling, you can have non-local coupling, where each of the oscillators are connected to a finite number of nearby oscillators. So local, non-local, global coupling, and you can introduce a coupling radius R equal to P by N, where P is the number of coupled nearest neighbor and N is the total number of elements. You can have different kinds of interactions, symmetry preserving couplings interactions, symmetry breaking interactions. So all these kinds of couplings then lead to very many interesting structures. Desynchronization, synchronization of different types, in-phase synchronization, out-of-phase, local synchronization, global synchronization when you have more than one population, local cluster synchronization or global synchronization, again, when you have more than one population, chimera states of different types, general chimera states, amplitude chimera states, or frequency chimera states, phase chimera, imperfect breathing chimeras, chimera-like states when you have more than one population, etc. You can have clusters, amplitude clusters, frequency clusters. You can have traveling waves, solitary states, steady states like amplitude depth, where dynamical state corresponds to equilibrium state, which is 0, or the steady state is in between two constant values, oscillation depths or chimera depths, so varying between two different states. Where chimeras, I didn't point out, chimeras corresponds to when you have n oscillators, few number of oscillators, finite number of oscillators are synchronized, where in the same system, same identical set of systems, the other class of oscillators are desynchronized. So coexistence of synchronized and desynchronized oscillations existing. So that's what chimera states correspond to. Similarly, you can have chimera death states, cluster oscillation death states, incoherent oscillation death states, and so on. They can be characterized. We have identified appropriate measures of characterizing these kinds of dynamical states you can start with standard deviation when you have the time series values, xj's, from numerical analysis, for example, you get starting from initial value x0, x2, x1, x2, etc. You can calculate the standard deviation difference in the state jth value of x from the mean value, and root mean square deviation you can construct. So sigma 0 corresponds to synchronized state, and sigma non-zero correspond to desynchronized, chimera, and other states. But you can have a better means of characterizing this by introducing the so-called local standard deviation, by first considering these time trajectories and take nearest neighbors, difference values, xj and xj plus 1. Consider rewrite the series instead of xj, you rewrite as zj by finding the difference values. And then considering dividing this time series into m number of equal number of bins, and then calculating the local standard deviation in each of these bins. And from this, one can calculate the strength of the so-called strength of incoherence. And S equal to 1 for desynchronous state, 0 for synchronous state, and it lies between 0 and 1 for chimera states and cluster states. And you can also distinguish between desynchronized chimera states and cluster states by introducing another strength of incoherence, S0, before removal of discontinuity points. And when you have such cluster states, you can identify, particularly in terms of these transformed variables, you can identify discontinuity points, and removing those discontinuity points, you have a strength of incoherence. And yes, after removal, you have the yes. So from these values also, for desynchronous state, both S0 and S as unit value, and for synchronous state, both S0 and S as 0 value, and for chimera states, it lies between 0 and 1. So in this way, you can classify the different kinds of dynamical structures that can arise in this class of one-dimensional arrays. But you can generalize this to spatially 2 dimensions, 3 dimensions, and so on, spatial higher dimensions. One can extend this notion of strength of incoherence in neuronal and ecological systems. We have identified in several classes of neuronal and ecological systems using this strength of incoherence and identifying appropriate spiral chimeras, and so on. Okay. I think I have already run out of time. Just I will take 2 minutes. So, you know, the single Stewart-Landau oscillator can be completely integrated by going to the spherical coordinates r and theta, and you can integrate and you can identify the supercritical bifurcations in such structures. So you have originally stable states, steady states, and then half bifurcation, and then you have limit cycle oscillation. So lambda negative, you have stable steady state, and then you have stable limits, half bifurcation occurs, and then you have stable limit cycle occurring for lambda positive, similarly lambda negative. So you can consider various kinds of couplings and symmetry preserving coupling. So this mean field coupling or symmetry broken coupling, for example, just the real part of Z bar and Z. And you can consider these kind of systems, and you can identify the kind of dynamics that comes out. And you can classify this in terms of the strength of incoherence. Standard deviation, it doesn't distinguish exact synchronized and desynchronized states can be identified, but the finer classification, chimera and synchronized states, etc., you require the strength of incoherence. And for classifying the cluster states, you require these 2 strengths of incoherence, removing the discontinuity point and without removing the discontinuity point. For example, for this class of symmetry preserving coupling, you have swing of synchronizations. Depending on the strength of isochronicity, you find originally you have desynchronization and then synchronization and then cluster state, then chimera states, and then cluster states, and then synchronized states. So starting from synchronized, you go through this change in the states, and then original states come back. So that is the kind of swing of synchronized states that can occur. This is for symmetry breaking states. Again, the different kinds of dynamical states. So this is the amplitude cluster. So here I have plotted in the first set, the variables xj are given. The second set, the frequencies are given. So here you have two sets of amplitudes. So you have amplitude cluster while the frequency remains the same, and amplitude chimera. So you see that in this globally coupled case that you have two kinds of states. One is coherent, the other one is incoherent, desynchronized states. Because of this global coupling, you can bring that back into two adjacent sets of states, that is coherent and incoherent for the amplitudes, whereas frequency remains unchanged. But here you have frequency clusters, both amplitude and frequencies you see in the form of clusters, and frequency chimera here. Both amplitude and frequency have two regions, coherent and incoherent regions. Similarly, for the broken coupling also, you get the same kind of states. So this can be all explained in terms of phase diagram of, for example, the coupling parameter epsilon versus isochronicity parameter C, and you see that depending on the values of and the regions A, B, C, you have different dynamical transitions. In the region A, as you move along, you have transitions from desynchronization, synchronization, amplitude chimera state synchronization. Whereas in region B, you have desynchronization, synchronization, amplitude chimera, amplitude clusters, and amplitude chimera states, and synchronization, and so on. So you can have different kinds of coupling that is possible, different kinds of transitions, which you can identify from the space diagram. Similarly, for the symmetry breaking coupling, you have the frequency chimeras, amplitude chimeras, etc., including chimera deaths that can arise. So various dynamical transitions that can arise in this particular set. Similarly, you can consider other kinds of interaction symmetry under non-local coupling, local coupling. So various kinds of interactions can arise, like transient breathing, stable amplitude chimeras, traveling waves, oscillated death states, and so on. And similarly, two interacting populations under global coupling, non-local coupling. So you have local synchronization, local chimeras, and complete synchronization, global synchronization, global chimeras, global synchronization, etc. The transitions can occur. Similarly, for other kinds of competing effects of attracting and repulsive, you have different kinds of dynamical transitions, which we have identified in recent times. Similarly, long-range globally coupled cell oscillator with symmetry breaking coupling. So you can have swing of synchronous state, solitary state, to cluster state, and so on. Similarly, other class of interactions, couplings, you can have different kinds of interactions. So to conclude, I have tried to point out that the study of collective dynamical states in nonlinear integrable, non-integrable, and chaotic systems continue to bring very many novel features, which can explain many natural phenomena and also can lead to novel applications, starting from hydrodynamics or optics, nonlinear optics, and ferromagnetism, or electronic cycles, and so on. So one can expect rich dividends coming from these studies in the near future. And I thank you all for your attention. Thank you very much. So I have taken, sorry, I have taken more than allotted time, and I have to rush through the last portion. But I think here I will stop, and I will try to answer some of the questions.
Okay, thank you very much for this very exciting tour through rather simple system which exhibit such rich dynamics and have so much importance for various applications. I see there are already several questions. I think Prasant Singh has.
Yeah, I can. Let me read.
But he can. Will you read? Prasant Singh, are you here? Will you read your question by yourself?
Yeah, I can read. So it says Prasant Singh has asked many questions.
Let's continue on one. First one.
Yeah, there is a study on bound states of 2 or more solitons. Can you elaborate? And is there a study on bound states of 2 or more optical bullets?
Yeah, but not all. Focus on one, please. On one.
Prasant Singh, yeah. Yeah, so bound states of 2 or more solitons in 1 dimension, you can consider. So for appropriate choice of soliton parameters, yes, you can construct bound states. For example, in the so-called LSRI, long wave, short wave resonance interaction. Recently, we have pointed out very many possibilities of such bound states, soliton bound states, soliton kind of molecules existing. So these bound states can be identified or studied for appropriate choice of the various soliton parameters. Solitons are characterized by this wave parameter, this propagation constants and other parameters. So for appropriate choice of these parameters, you can have bound states. But for optical bullets, so these studies have been being taken up only in recent times. So I have shown 2 cases where one can have bullets colliding. After collision, they come out without change of form or even diminution of speed, I may say. But for other cases, when this appropriate parameter condition is not satisfied, they undergo the collision scattering and they separate out into filaments, chaotic filaments. So it's not clear whether one can have bound states for such systems. So one has to undertake very careful numerical analysis in order to identify such the possibilities of such bound states. But I think in one of the slides, I tried to point out kind of bound states with breather-like bound states that can exist. So even in higher dimension, there is possibility of identifying such bound states, but in my understanding is that the study is not that complete. The next question is, sir, I can imagine 2 types of optical solitons, one localized electromagnetic field in laser light, and another is like mode lock light pulse, which is isolated on moving isolated. Is there characteristic difference in these 2 solitons? Will their governing equation be seen? I really do not understand this question. So I can imagine.
Please, Lakshman, we should not only let one guy asking 100 questions. We have also others.
Yeah,
there was one from the chat.
Yeah, anonymous attendee. Equations giving birth to bullet kind of solution are not integrable. It is not then should be considered bullets as 3-dimensional soliton or not. Yes, these 3-dimensional equations, the integrable soliton equations in higher dimensions, in 2+1 dimension, there are certain equations, but they exhibit exponentially localized solutions called dromions and so on, or lime solitons. But the kind of bullets which is admitted by the kind of nonlinear Schrodinger equations I showed, that equation, to my understanding, is not integrable. One can carry out the so-called Payne-Levé type analysis, and then one can make sure that it's not integrable. So if it is not, then should we consider bullets as 3-dimensional soliton or not? Well, from my point of view, the numerical analysis for appropriate choice of parameters shows that these bullets under collision, they retain their shape and even speed, etc. So they do not lose energy under collision. So it is a kind of soliton, three-dimensional solitons, but is it an integrable dynamical system? It appears to be not, but still under appropriate conditions, it can admit stable bullets which can undergo collisions. So this is the kind of soliton-like, I may say, in three-dimensional soliton-like structure that one identifies. I do not know how this can be related to integrability. So, as I said, the system as such appears to be not integrable. It doesn't have integrability, means sufficient number of integral sum motion commuting integral sum motion. Such integrals do not seem to exist, but one has to very carefully analyze these structures further and whether one can have three bullets, like three soliton solution. Can one have three bullet collisions possible and n bullet collision possible and so on. So one has to further carry out very careful numerical analysis before coming to a conclusion whether it will be called, it can be called soliton. So I think at present, I will call this as a bullet in three dimension, retaining its structure. Yes. Again, there is a question by Prasant, but before that, Asit Saha. Sir, how to explain?
Wait. I would add a question to this. This is to Asit Saha. He asked for Rack waves and high amplitude. And I have the question, what are the necessary conditions for Rack waves?
For rogue waves. Yeah,
it's a bit related. If you can.
Yeah. Rogue waves. How? I mean, as I can see, the nonlinear Schrodinger equation, the single nonlinear Schrodinger equation itself can admit rogue waves, and rogue waves are generally defined as waves which suddenly appear from nowhere and disappears suddenly. So it exists only for short time in short space, but that occurs as a limiting form of the so-called breather solutions, which go to non-zero values at infinity, large values of space and time. So I think my understanding is that rogue waves can exist as limiting forms of certain breather-like structures. I think that is the condition for rogue waves with very high amplitude to exist.
Okay. Then maybe Senthil Kumar.
Yeah, next question is Senthil Kumar, C. Senthil Kumar. I have a fundamental question. In a billiard ball collision, there is no phase shift, but in soliton collision, there is a shift. Well, I'm not sure. Billiard ball collision, there is absolutely no phase shift, because when they collide, they undergo change in the direction. So I think that corresponds to phase shift. So it is not that the same two billiard passes through. I mean, it's straight passing through collision. It's not straight passing through collision. There's change in the direction, and that corresponds to phase shift. So that's my answer to Senthil Kumar. Then Saravana Veni.
Yeah, please.
Some 1+1 dimensional system exhibit Dromaeon solution. Likewise, whether soliton bullets. No, 1+1 dimensional systems cannot exhibit Dromaeon solution. 1+1 dimensional systems exhibit only soliton solution, that is localized structures. Dromaeons, what I mean is, if you go to 2+1 dimension, you can have exponentially localized solutions in both spatial directions. So those are called Dromaeons. The soliton bullets exist for 1+1 dimensional equation. So by bullets, I mean it's 3 dimension. or you may call in 2 dimension the corresponding disk-like structure. So by Bullet, by definition, it's a 3-dimensional spherically symmetric structure that I'm considering. So if you consider 1 plus 1 dimension, so it's a localized structure. Okay. So exponentially Gaussian-like structure you can think of. So Gaussian type collision solitons one can identify even in 1 plus 1 dimension. Yes.
Okay. May I ask another question also about dissipative systems, almost about the others. You mentioned these extreme events.
Yes.
And what is the general mechanism that extreme events occur in dissipative systems?
Yeah, I mean, as far as I can see from the examples that from the various examples that have been considered, even at the single oscillator level. So whenever you have sudden change in the attractor, if it occurs, a crisis occurs, then there is a possibility of extreme events taking place in the neighborhood of that crisis state, the parameter value at which the crisis state has occurred. So this at least has been checked in a few parameter values for the Liénard type oscillators by Chandrasekhar et al. And by Leo Kingston and so on. And in the case of rotating parabola system, again, whenever there is a sudden change in the nature of attractor, in that neighborhood, extreme event seems to take place. If you look at the corresponding statistics of the events, so Venkatesh, Sudarshan, Senthilvelan, etc., they have identified extreme event in that example. And we have a few other systems where such extreme events occur whenever there is a sudden change in the nature of the attractor. So that is the answer I can give you for the possibility of occurrence of extreme events in a single oscillator case. And in coupled systems, perhaps similar conditions one may be able to identify, I think.
Okay, yeah. Thank you very much. I think our time is almost over. There are some questions, but I think people can directly contact to Professor Lakshmanan afterwards, and you can have discussion about further details about NLSE, etc. I think now it's time to thank you very much. It was really a great event again, and please come back in about 4 weeks to our next meeting. And I'm very happy that we had such a great event today. And thank you very much, all of you, but mainly, of course, to Professor Lakshmanan. Bye.
Thank you very much. Thank you.